second speaker has 2 first names and 2 last names, but I believe he goes by Stathis Chrontsios. So it's my pleasure to introduce Stathis from University of Illinois Urbana-Champaign, and he will talk about Assouad dimension and quasi-conformal maps.
Yeah, thanks.
Thank you, Dimitris, for the introduction, and I would like to thank the organizers for the invitation. I will be talking about Assouad dimension and spectrum under quasi-conformal maps. This is joint work with my advisor, Jeremy Tyson. Can everybody see my screen?
Yes.
Yes.
Perfect. Let me hide this. Okay. So during the talk, I will introduce first the different notions of dimension that we will be talking about: the Hausdorff dimension, the box counting, and the Assouad dimension. Then I will introduce the Assouad spectrum and some of its properties. I will move on to introduce quasi-conformal maps and how they distort these notions of dimension. The distortion of Hausdorff and box counting dimension are known results. Our main result is the distortion of Assouad dimension and spectrum under quasi-conformal maps. And I will also show how we can apply our main result to classify polynomial spirals up to quasi-conformal equivalence. I will finish the talk with some remarks and open questions that follow naturally from this discussion. So let's start with the Hausdorff dimension. In order to define it, we will need the R approximate S-dimensional Hausdorff measure of a set that is defined to be the infimum of the sum of all diameters of UI to some power S, where UI forms a countable cover of F, and every set UI has diameter at most R. If we take R to go to 0, in that case, we get the S-dimensional Hausdorff measure of a set. And we define the Hausdorff dimension in a natural way. We define it to be the infimum of all S for which the S-dimensional Hausdorff measure of the set is 0. So it's the same idea as to why we call a square two-dimensional. It has surface area, it has infinite length, it has 0 volume. Let's see some examples. Of course, the unit square has dimension 2. That should be expected. The set 1 over n for n all natural numbers union 0 has dimension 0. And that is because Hausdorff dimension comes from a measure. So a countable set will always have dimension 0. The counter set is usually the first fractal people see when they take a real analysis, for example. It is a set with Hausdorff dimension ln2 over ln3, which is between 0 and 1. So it's not quite just a bunch of points, 0-dimensional, but it doesn't quite has length. And the Sierpinski carpet is a similar fractal in R2. It has Hausdorff dimension ln8 over ln3, strictly between 1 and 2. Let's move on to the box counting dimension. So this is defined for a bounded set, and it will become clear why. Denote by NFR to be the smallest number of sets of diameter at most R we need to cover F. The upper box counting dimension of F is the lim sup of log NFR over log of 1 over R. If we replace lim sup by lim inf, we get the lower box counting dimension. If the two are the same and the limit exists, that's the box counting dimension of the set. I will only be calling this now box counting dimension from now on for the rest of the talk, because for the sets we will deal with the the limit actually exists. So if it doesn't, we only care about the upper box counting dimension anyway. And this makes it somewhat clear why we define this dimension only for bounded sets, because this would be always infinity for unbounded sets. Now, an equivalent formulation is to define the box dimension as the infimum of all exponents alpha, for which NFR is at most R to the minus alpha up to some global constant, for all R that are meaningful, for all R less or equal to the diameter of F. If we replace this notion of NFR, and sometimes it's convenient to do so, by the smallest number of dyadic cubes of a certain size instead of arbitrary sets of diameter at most r, we get again the same thing with the same notion. So if our set is this and we don't use, let's say these are the axes, and we don't use sets of diameter r, but we start subdividing, let's say, a cube that includes our set into smaller and smaller cubes, and we create a grid. In that case, if we replace NFR by the number of cubes that that's our set, in either of the two formulations, we get the same thing. And I will repeat that again for the Assouad dimension, more formally probably. Now, it's easy to see that the R approximate S-dimensional Hausdorff measure of F is bounded above by R to the S times NFR. So this gives the relation between Hausdorff and box dimension immediately for all bounded sets F. A few examples. The unit square still has dimension 2 under this notion as well. No, this is the Sierpinski carpet. The Sierpinski carpet also has the same dimension, same box dimension as the Hausdorff dimension. Now that set we defined though, and I will write it again, 1 over n for n all natural numbers, union 0. This set now has box dimension 1 over 2. So the box dimension does not come from a measure. And in fact, if we take a look at our set, 0, 1, 1 over 2, so on, around 0, we will start needing more and more sets of smaller scales, but we will need more than we would for just a countable set spread out on the real line. So that's the intuition of why the box dimension is not quite 0 as the Hausdorff dimension is. And another example that we will talk a bit more about even later on is the polynomial spiral SA for some positive a. It's defined to be t to the minus a times e to the it on the complex plane for t greater than 1. This spiral was proved by Fraser to have box dimension given by this formula, the maximum of 2 over 1 plus a, comma 1. And it seems natural in a way, because how do these spirals look? They accumulate around 0, and the smaller a is, the longer they take around 0 to accumulate. So if a, for example, is something bigger, that spiral would look something like this. It would go to 0 much faster. So this is encaptured in the definition, in the formula for the box dimension, since if a is small enough, the box dimension becomes bigger and bigger, since we get more and more of a two-dimensional like set around 0. So if one picks a, for example, strictly less than 1, the Hausdorff dimension of the spiral still remains 1, but the box dimension is something greater than 1. So we have examples where the box and Hausdorff dimension differ. One more notion of dimension, it's the Assouad dimension. And if one has not seen this definition before, it does look complicated, but I will explain what it basically says. It's the infimum of all exponents alpha, for which there exists some constant, such that for all scales and all points at all places on F, the number of sets of diameter at most the smaller scale that we will need to cover what we see of what part of the set we see inside the ball of the bigger scale is bounded above by C times the ratio to the exponent alpha. Now, what does this say? This says that if you have a set, at all points, at all places on the set, you are allowed to pick some R, and this R tells you how much you are allowed to zoom in on that set, on that point, or zoom out from that point. So for example, if you have a set that, like the spiral for some big A that accumulates very fast around 0, if you start taking R smaller and smaller, you will eventually see the spiral accumulating slower and slower in a way, right? And that would be as if we are zooming in at 0. Or at the same time, for example, if you have that other set we defined, 1 over n is natural from 0 to 1, if you get some R that is small enough, then you will start seeing more and more and more and more points. So you will start seeing something almost one-dimensional every time you zoom in more and more. And the same goes for zooming out from sets. This is the idea of the Assouad dimension. Now, from the second formulation for the box dimension, one can easily see that the Assouad dimension is the greatest dimension of them all for bounded sets F. And if we take a look at a few examples, the unit square has dimension 2 as it's expected to have. The Sierpinski carpet also has the same Assouad dimension as its other dimensions. That also shouldn't be too surprising because wherever we zoom in or we zoom out from the Sierpinski carpet, we get more or less the same set, the carpet again. So it makes sense for the dimension, for the Assouad dimension to be the box dimension. For that set, 1 over n, I will write it 1 last time. F equals this set. Now the Assouad dimension is equal to 1. The box dimension, remember, was 1 over 2. Oops. And the Hausdorff dimension was 0. And that comes from the intuition I just mentioned before, that if we zoom in a lot at 0, we will start seeing so many points that will need sets of diameter at most a small scale, as many as we would need to cover a small line segment. So in terms of Assouad dimension, this set is as if it has some length. And for the spirals, same idea. If we start zooming in at 0, we will see the spiral, no matter how fast it goes to 0, we'll see the spiral accumulating slower and slower, the smaller capital R gets. So for a less than 1, we have strict inequality between all the dimensions for the spiral. Now, the breadth, we're not done with the dimension notions yet. There is still the Assouad spectrum. Now, the Assouad spectrum is a set of many dimension values, and we get it by fixing first some theta between 0 and 1, and we define the regularized theta Assouad spectrum, which I will be calling just Assouad spectrum from now on, to be the infimum of all exponents alpha, for which again the same thing holds true as in this definition of the Assouad dimension. So for all scales and all places, we need this covering number to be at most the ratio to the exponent alpha, with the only difference that now we require this relation between the smaller and the big scale. We need the smaller scale to be at most r to the 1 over theta. The idea is again the same. It's only just, it's about zooming in and zooming out from sets, from parts of the set, but we have to keep in mind this restriction on the small scales we choose. If now we basically replace this by r less tilde 1 over theta, where this is a global fixed constant, we again get the same notion. And as I mentioned for the box dimension, now we can replace this covering number by the covering number relating to the dyadic cubes. And let me make this more specific now. We pick a point on our set, X, and we have a ball centered at that point of radius R. What can we use instead of the smallest number of sets of diameter at most R? We can use the smallest number of m dyadic cubes. So if this is bxr, we also have the cube qxr, and the zero dyadic cube is just qxr. The one dyadic cubes are the ones with side length. Maybe we should write that down. One dyadic cube has side length 2 to the minus 1 times 2r. The two dyadic cubes, we go even further one level, so we get even more. At each time we subdivide, we get 2 to the n cubes. So the two dyadic cubes have side length 2 to the minus 2 times 2r, and so on. And if we have our set F now in there, this color, we count each time for each level how many of these cubes would we need to cover it. This many in this case. All right, so if we replace this covering number by nd, we get again the same notion. Notice here that everything is more or less the same. This is the smaller scale, and this is r over the smaller scale to the alpha. Everything works just as it's supposed to. Now, some of the examples for the spectrum. The spectrum for any theta of the Sierpinski carpet is ln8 over ln3 again. For that set 1 over n union 0, it's actually given by this formula 1 over 2 times 1 minus theta, the minimum of that and 1. And this is a value for each theta that fluctuates between the box and the Assouad dimension. For the spirals, Fraser proved that this is the formula that spiral of a given A satisfies. And as you can see, the formula changes depending on how slowly the spiral goes to 0. And also, it might be a bit difficult to notice it in this formulation. I will later rewrite this formula for the theta spectrum of the spiral. But when do we get 2 and when do we get this formula? Well, the phase transition in this case would be A over 1 plus A. So for theta less than that, we get the formula. For theta greater or equal to that, we get just 2 for both of the branches. So if we choose theta to be less than A over 1 plus A, less than the phase transition, we actually again have the spectrum to be strictly between the box dimension and the Assouad dimension when A is less than 1. Okay, some of its properties, if we fix theta and we look at the spectrum as a set function, we map the set to a value, then this function is monotonic. It is finitely stable, something we should expect dimension notions to satisfy, meaning that the theta spectrum of the union of E and F is the maximum of the two spectra. It's also invariant under taking closures, so the theta spectrum of F is equal to the theta spectrum of the closure of F. And it's also, oops, this pose is missing. It's also invariant under by Lipschitz maps. So the theta spectrum of F is equal to the theta spectrum of G of F, where G is a by Lipschitz map. Now, if we fix F instead and look at it as a real function, that is a non-decreasing continuous function on the open set 0, 1, and in fact, it's even Lipschitz on compact sets of compact subsets of 0, 1. So if we now fix a bounded capital F and we take the limit theta goes to 0 of the theta spectrum, we get exactly the box counting dimension. If we go the other way, if we take the limit theta going to 1, we don't get the Assouad dimension every time. We get something called the quasi-Assouad dimension, which can in fact be defined this way. I don't want to say too many things about the quasi-Assouad dimension since we won't be using it. And for our purposes, for the rest of the talk, actually the limit theta going to 1 will be the Assouad dimension. But for the sake of completeness, I will write this inequality involving all of the dimension notions so far, well, plus the Hausdorff dimension, which is the smallest one of all of them. So we have the Hausdorff dimension being less or equal to the box counting, being less or equal than the theta spectrum, less or equal than the quasi-Assouad dimension, less or equal than Assouad dimension. And as we saw, we have strict inequalities for all of these. Before I move on to the quasi-conformal maps discussion, are there any questions on the notions of dimensions? Okay, perhaps I should go ahead then and start talking about quasi-conformal maps. The seminar is called quasi-world, so I think that most people know what a quasi-conformal map is, but I will still introduce it. It's a homeomorphism between domains in Rn that lies in the local Sobolev space W1n, and there is some global constant k for which the matrix norm of the derivative to the power n is at most k times the determinant of the derivative, and this needs to hold almost everywhere in omega. If we now take the smallest value k for which this inequality holds true, that is defined to be the outer dilatation of f. A few examples, both on the complex plane. If we take x plus iy and map it to x plus kiy, or we do the same thing for the real part, then both of these are quasi-conformal maps from the plane onto itself. And a particularly useful quasi-conformal map, which we will use for our application later, is the radial stretch map, mod z to the k minus 1 times z. Again, this is a k quasi-conformal map from C onto C. Okay, so one might naturally ask, how do these maps change the dimension or the notions of dimension we saw? Before we state even known results, we need to talk a little bit about this higher integrability exponent. Namely, we define for some fixed n and some fixed k, p and k to be the supremum of all values p for which there is a constant, such that for every quasi-conformal map with outer dilatation at most k, this estimate, this reverse Helder inequality, holds true for every cube that is deep enough inside the domain of f and has and the double cube has image that is deep inside the target of f. And by double cube here, what do I mean? I mean that if we have q to be q comma qx comma r, 2q is just the cube centered at the same point, but with side length, well, I guess 2 times what we had before. And the same goes for ball. So we have the ball bxr, 2 times that is bx 2r. So we define this exponent as this supremum, p and k. Gehring in 73 showed that this is greater than n for each n greater or equal to 2 and for each k greater or equal to 1. Astala gave a formula for this exponent in the case of n equals 2, namely it's equal to 2k over k minus 1. For dimensions greater or equal to 3, this exponent remains conjectural. People believe it to be equal to nk over k minus 1, but it has not been proved yet. So now that we defined this higher integrability exponent, we can state results for the Hausdorff and box dimension. Namely, Gehring and Väisälä proved that if we have a subset of omega, which has Hausdorff dimension equal to some alpha, then the Hausdorff dimension of the image of that set is bounded between these two values, which include this higher integrability exponent, namely it's bounded above by p and k times alpha over p and k minus n plus alpha for any k quasiconformal map. And in fact, you notice here this k to the n minus 1. That is because if we prove this side for f and we apply it to the inverse has outer dilatation that is at most the outer dilatation of f, the n minus 1. That's where this is coming from. We basically apply the same inequality to the inverse and get the lower bound. Now, these estimates, we sometimes like to write them in the symmetric form involving this h of p. So we define h of t to be 1 minus n over t. And when for some Sobolev map, let's say W1p, this h of p is in fact the local Helder continuity exponent. And we like to see how it gets involved in this dimension distortion. That's why we sometimes write these estimates in the symmetric form. Keep in mind that from here, which was the estimate for the image for just f, we have it now on the left-hand side. I will be clarifying that when it's needed. So that was the Hausdorff dimension. For the box counting dimension, Kaufman, about 30 years later, showed that for a bounded subset of omega, again, the exact same inequality holds true, replacing the Hausdorff by the box dimension. And that's literally the only difference from the previous estimate. Now, it's important to point out that both of these results, if we replace P and K by P, they actually hold true for any Sobolev map in W1P, not necessarily quasiconformal. We proved similar estimates now for the Assouad dimension and spectrum quasiconformal distortion. Namely, for the Assouad dimension, we showed that if we have a K quasiconformal map between domains in Rn, and E is a compact set satisfying Assouad dimension equals to alpha, again, the estimate is identical, meaning that wherever we had box dimension before, now we have Assouad dimension. And in fact, if omega is equal to omega prime equal to Rn, the conclusion holds for all E, not necessarily compact. Before I state the theorem for the spectrum, the naive approach would probably be to just think, okay, maybe the same estimates holds true for the theta spectrum here. That would not be quite right, because this variable is a variable that tells us the relation between the two scales, and the quasiconformal map can change those small scales. So we can't really expect to have the same theta in both sides of the estimate. Having said that, let us see what the result actually is. If we have a K quasiconformal map as before, and we define theta of t to be given by this formula, 1 over 1 plus t, then for a compact set, E inside omega, we have, yes, the same estimate, but the theta parameters change. And this basically tells us that when we apply, so this is the estimate for f, when we apply f, we somehow multiply these estimates by k, these parameters, sorry, by k. But other than that, which is a difference that we were expecting, the estimate looks very similar to the estimates we had before. We will need a couple of properties of quasiconformal maps to sketch the proof of our result. The first one is a very known principle. It's the egg yolk principle. And it basically says that if we fix n and we fix k, there exists an increasing homomorphism eta that depends only on k and n, for which every K quasiconformal map in Rn and any cube that is deep enough inside the source, the restriction of f in Q is zeta quasi-symmetric. And what does that mean? It means that for any distinct triplets, the map satisfies this, this inequality for the distances of the points versus the distances of the images of the points. And this can be stated for balls as well, not just cubes. A corollary of this looks a bit technical. I will explain how we see it, what's the intuition behind it, and why we need it. For each n and k and c, we will see what this c can be chosen to be. There exists some k such that if F is a K-quasiconformal map between domains in Rn, and Q is a cube that is K deep enough inside the source, then there exists a cube Q prime in the target that is C deep in the target. That's how we pick this C. That's how we choose it. We decide how deep do we want Q naught to be in omega naught, Q prime in omega prime. And what is the relation involving that new cube? It's in fact in between the image of the Q under F and the image of the cube K times Q under F. So this basically tells us something that we know about quasiconformal maps, that cubes under a quasiconformal map behave more or less like cubes in a more technical way that we will use in our proof. So I think it will probably be nicer if I sketch the proof first. I have the slides with the details in case people have specific questions, but I think it will be nicer if I draw some things first and explain the main idea. So what do we want to prove? We have the Assouad spectrum, the theta of we want to show that the theta of the Assouad spectrum of f of phi is bounded by something. Again, we will prove it for just f and apply what estimate we get to the inverse and get the same result, the other estimate, so the result of our theorem. But I would prefer to write this in the non-symmetric form because we want to clearly see what bound we want for the exponent of that ratio of covering scales. So we will bound this by p times alpha over p minus n plus alpha, where p is something less than the higher integrability exponent, p and k, and alpha is something bigger than the Assouad spectrum that we have on the other side of the inequality, namely the theta of t over k Assouad spectrum of E. If we prove this, and let's call this value just vita, if we prove this for this choice of p and alpha, for this arbitrary choice, and take limits, we would actually get our estimate. Okay, so how do we start? Suppose we want to bound the Assouad spectrum of the image. So suppose this is f of e. We pick a point y on f of e, and we pick a radius r prime. So this is b y r prime. And if we bound the number of small scales we need above by the ratio of the scales to, well, to just vita, we will in fact be done. Now we can start working on this by choosing specific scales, and the scales we will choose that are convenient for our arguments are the ones that 2 to the minus m times alpha over beta times r prime. So if we look a bit into the future, what we will be getting is we will be getting this sort of thing to the beta. This is what we would like to get. So this, if we do the calculations, would in fact be just 2 to the m alpha, which would be, ideally, we want to get this bound from the bound for the theta Assouad spectrum of the source of E. So we will choose scales Rm without the prime, so that this is the ratio of the scales to the alpha, which is a number greater than the Assouad spectrum. Okay, so we need to use this kind of scales in the source. So let's apply the inverse map on what we have already to start working in the source where we have more information. Let's say now that this is E. Of course, under the inverse map, and X is just the inverse image of Y. Under this inverse map, we don't have this ball to be a ball anymore. It's some kind of set, but this is X. But according to our corollary, we in fact can find some ball that includes this set according to the information given by just NK, and we can decide how deep we want that to be inside omega. So let's call this ball BXR of radius R. And it does not have to be too big either. That's what that corollary says. Now, if we start working on this ball and we start working with the radii with a scale that are equal to 2 to the minus m times alpha times r, oops, not alpha, sorry, no alpha needed here. We can in fact start working with dyadic cubes instead because of the equivalent formulation of the spectrum and the dimension. So that will be convenient because we have an exact control of what sets we use, at least in the source. And we also can use inequalities that we know for cubes, namely Morey-Sobolev and Rivers-Haldane inequality. It will become clear again once I write things down. So we will start working, let's say, with dyadic cubes of this cube QXR. 2 times Rm is the side length of its M dyadic cube. And we'll start subdividing. Now, if we get a cover consisting of dyadic cubes of E inside BXR, and we take again the image, we apply F on that, we would get some covering. So we would get some sort of covering for what we see inside BYR prime of F of E. However, the problem is that if we do that for every scales, we need to do that for every scales, but there might be some cubes that are not quite small enough. They might have diameter that is not at most R prime M. Well, let's call minor, let's say Qi is minor if the diameter of the set we get when we apply F to that cube is at most R prime M. Those cubes we can use straight away, and we can count them because we can count how many cubes we need here. We would need approximately, or at most, R over Rm to the alpha, which is just 2 to the M alpha. Again, by just what alpha was defined to be greater than the spectrum. So those cubes we can count and we can leave them alone. They are sets that have diameter at most this when we apply F. The major cubes are the ones that might be a problem, namely the cubes for which the diameters are more than R prime M. What do we do in this case? When we have a major cube, since F is uniformly continuous, we can keep subdividing the cube until we get small enough sets in the source, in the target actually for F. However, we can't do this for as many times as we like because we want these relations to hold for all meaningful M, not just some arbitrarily large M. So we will need to count how many times we have to subdivide a major cube in order to get only minor cubes whose parents are major. how do we count those cubes? Well, one of the tools we have is the Morey-Sobolev inequality, which says that the diameter of f of qi is at most some constant times the diameter of qi to the 1 minus n over p times the integral of the qi of the derivative, the p, whole thing to the 1 over p. So for major cubes, we actually have that this is at most r prime m. So we can now forget about this for a while. And if we sum over all cubes, all major cubes, we do get an estimate on the left-hand side. We would get the number of all major cubes that might appear, bounded above by some quantity here. The problem is that now we have two different scales. We have r and r prime. So if we do that, we would basically get, let's say n is the number of all major cubes, bounded by some other constant, times something that involves both r prime, in fact, to the minus p, and r, in fact, to the, I believe that is p minus n, times some power of 2 with convenient exponents, times the LP norm. And in fact, if we were trying to bound the box counting dimension, in this case, we would be done. And that is actually the proof of Kaufman's estimate. That is because for the box counting dimension, we can formulate almost everything more or less the same way, but we don't have these bigger scales to deal with. They are just the diameters of the set. So they are just some constants. But here we have to be careful. This is where the reverse Helder inequality comes in. So let me rewrite that. This was the average over qi of the p, the norm of the derivative to the p, whole thing to the 1 over p, less or equal than some other constant again, times the same average, the double cube, but now to the n, the whole thing to the 1 over n. Now we can use this estimate, and this is the trick for the Assouad spectrum in our proof, to bound this integral by something, by some constant times exactly what we need to get rid of the scales. So this is bounded by something like that. And this is true, first of all, because of all qi's lying in qxr. And once we have that, we actually will have some estimates. And by definition of all the exponents alpha and beta, we in fact get a bound involving just 2 to the m times alpha times some constant that depends only on p, n, and f. And now we have bounded the number of all major cubes that appear. We don't want to use major cubes, but every time we subdivide a major cube, we get at most 2 to the n minor cubes. So in fact, just changing this constant by multiplying it by 2 to the n would result in the bound that we like. So this is actually beta, I think. Yeah. So we have bounded all the number of all cubes we need here, that when we apply f, we get them to be sets of diameter at most this in the set that we want to cover. We have bounded it by some constant times 2 to the m times beta, which bounds the theta Assouad spectrum of f of e. Now, obviously, I put a couple of things under the carpet. First of all, I did not talk about how these scales relate. The quick answer to that is that it's coming from the Helder continuity of f, the local Helder continuity, and that changes the scales in a way where they relate like that. So that's where the change in the scales comes in. I think I should probably move on to the application at this point. I do have the slides and a few technical things we have to do in the beginning to make sure all the inequalities are usable, namely to have both E and F of E deep inside a specific cube. That can be done by the Lipschitz invariance of the spectrum, by using Whitney decompositions and the egg yield principle. But we can talk more in depth about this if people have questions. So let me skip the slides that involve the proof and let me go to the application of our theorem. Namely, for A greater than B greater than 0, there exists a quasiconformal map F that maps SA, the spiral SA, to the spiral SB, if and only if the outer dilatation is at least A over B. Now, one direction is easy. Yes, we can find the quasiconformal map that maps SA onto SB and has outer dilatation at least A over B. Namely, that would be the stretch map mod Z to the 1 over K minus 1 times Z. And that map does exactly what we want it to. So that direction is clear. The other direction, suppose towards contradiction that K is less than A over B and there is a K quasiconformal map that maps SA onto SP. For that, since we are in the planar setting now, we can use Assouad's formula for the higher integrability exponent. And if we plug that in Kaufman's estimate, we get this inequality involving the box dimensions. If we plug in the dimension formula proved by Fraser in that estimate by Kaufman, we get that K actually needs to be greater or equal than the minimum of A, 1 over the minimum of B, 1. And if A and B are both less than 1, we would be done. But that doesn't resolve the problem in its full generality. To fully solve this problem, we would need a couple of values for the spectrum. So I rewrite here the formula for the spectrum of a spiral SA, making it visible where the phase transition happens. And by choosing T over 1 over B, then theta of T is B over 1 plus B. So for the theta of T spectrum of SB, that would be exactly equal to 2. Whether in either case, whether B is less or equal to 1 or B is greater than 1. At the same time, the spectrum in our theorem for SA would be the theta of T over K spectrum. And if we plug this in, we get something that is strictly less than the phase transition for the spectrum of the spiral SA. So we have that this spectrum is strictly less than 2. But if we plug in Assouad's formula in our theorem, we get that basically this cannot happen. We get on one side the theta of T spectrum of B to give 0, and this is a strictly non-zero quantity. So there's a contradiction. There can be no such quasiconformal map. Let me finish up. Let me wrap up the talk with a couple of remarks. We can actually improve Theorem 2 and Theorem 1 a little bit by using the P sub I and K integrability exponent. That is the exponent defined exactly the same way as P and K, but involving the inner dilatation, K sub I. And while to get the other estimate, we just applied the estimate we proved to the inverse. For this, we will need to redo the whole proof for the inverse, but it goes to exactly the same way. It's important to mention that the box dimension distortion theorem was useful for the quasiconformal equivalence. It was not enough. We needed some value from the spectrum as well. And the Assouad dimension alone was not enough either because it's 2 for all of the spirals. The same is true for the Lipschitz classification of the spirals. Namely, one can prove that SA is Lipschitz equivalent to SB if and only if A is equal to B. And in that case, again, we will need a value from the spectrum. And one can prove the same thing for elliptical spirals, but I won't state that. And the theorems for Hausdorff and box dimensions were true for Sobolev maps also, not necessarily quasiconformal. Our theorem specifically used the fact that F is a quasiconformal map. So a natural open question to ask in this case is what happens for f in W1P that is not quasiconformal or not even injective? How does such a map distort the Assouad dimension of the Assouad spectrum? Another question is under what other classes of maps can we investigate the same problem? Namely, what are other classes that classify things? People are interested in classifying things with them, and we can investigate how the distortion, the dimension distortion works and apply that for classification problems. These are the main results in case someone wants to be looking at them while they ask questions. Thank you so much for your attention.
Yeah, thank you. So let me open the discussion. Are there comments or questions? I mean, one natural class of maps that are very close to quasi-conformal maps are maybe quasi-regular maps. So what about distortion estimates for these maps?
Yeah, I don't think there are. That's a good question. I don't think there are estimates, as far as I know, for at least the Assouad dimension and spectrum. I would imagine it would be probably maybe an easier problem than the W1P. But yeah, that's definitely an interesting class to be looking at. Yes.
Are there other comments or questions?
Yes, I have a question. So thank you, first of all, for the talk. Very, very interesting, very well explained. So do you know what are the weak tangents of a set? When you zoom in a set, it's precisely what you explained with the set 1 over n, 0. So at the point 0, the weak tangent seems to be an interval. It's not so it's a set with interior, and this probably explains why the Assouad dimension is 1. Is this correct?
Yes, that's correct.
So
And one can even, yeah.
So is it in general true that if you have a set where the blow-ups or the weak tangents have a certain dimension, I don't know, Hausdorff or whatever, then the Assouad dimension will be larger than all the dimensions of the blow-ups?
Yes, that is actually true. And one can even define the Assouad dimension of a set X to be the supreme of all the Hausdorff dimensions of weak tangents of X. So that's in fact, yes, that's correct. It's another definition for the Assouad dimension.
And what about the Assouad spectrum? Can you also find a similar definition?
For the spectrum, I would imagine that things are a bit trickier because of the relation of the scales. I know that Fraser does have a couple of remarks in his book about the spectrum and the weak tangents. I don't think the relation is as nice as this one. But yeah, that's a good question. I think there is some relation, not as clean though, for the theta spectrum.
Okay. And also a final question, again related, because quasi-conformal maps are also locally quasi-symmetric. Could there be some alternative argument using blow-ups for at least for the distortion of the Assouad dimension? So maybe there could be an alternative argument where you blow up your map and the sets and you go to the tangent spaces and then you see how the map distorts the Hausdorff dimension of the blow-up.
So you're asking if there is some similar estimate for just quasi-symmetric maps, or
no? If there is an alternative proof of your estimates for the Assouad dimension.
Oh, I see.
By using the blow-ups.
I see. Well, our proof relies on the on the definitions, on elementary things, more or less, and those two inequalities. I have not thought of that. That is very interesting. It could very well be. Yeah, it could very well be, because quasi-symmetry, we use quasi-symmetry, and yeah, that I wouldn't be surprised, actually. I would be interested to look into that.
Other comments or questions?
Maybe a very quick, a small comment or question. So you had the nice application of this Assouad spectrum to proving when the SA and SB are quasi-conformal, or for which K they are quasi-conformal. I was wondering, is there a way of, have you thought of also a different proof using maybe modulus, or is it possible, similar to rectangle? It would seem like if the spiral is winding a lot denser, then you'd have some rectangle being stretched a lot into the spiral, or perhaps some kind of argument like this. I haven't thought the details, but do you see
so in fact, once we proved our theorem and we applied it for the spirals, we thought of the exactly same thing.
Yes.
It seems to be very difficult. So we were not able to come up with a proof just using the definition of quasi-conformal. It seems to be difficult.
Interesting. Yeah.
So it's yeah, this proof involving the dimensions seems to be a lot cleaner.
Well, this sounds like a nice challenge to come up with a modulus for.
It does. It does. Yeah.
So, are there other comments or questions? Well, that doesn't seem to be the case. So let's thank Stati.